Hello, good afternoon, good morning. Today we will be demystifying a number of things that have been said these days. Those of you who are expecting music during my presentation this year, there will be no music. I want to make things easier for the organization. I just don't want them to go into any intellectual property issues. And even if we like the offensive side a lot, and I've been talking about the offensive side a lot, I also would like to focus on the defensive side. So it is also very important to learn more about the technology and to see the level of progress so far. As Roman mentioned on day one, apparently, well, most of the rooted budget this year goes to the room, which is allocated to this room. So you may notice that in the headrest of your chairs, you have a system similar to that of the Matrix, so that we can inject them as much knowledge as possible over an hour. That is to say, the knowledge associated with the knowledge sharing. So I hope that you had a strong coffee, anything that you need to survive the next hour. So we will be here, the 900 of us in this room, and because we will be here for an hour, 900 people, so hopefully this will help you optimize your knowledge. It's knowledge about a protocol which seems to become really fashionable very soon now. So first of all, we will see of how we made it to where we are. We will be talking about messaging communication. Later on, I'll give you a brief introduction about crypto that will give you the context for the second part of my presentation, and then we will focus on the signal protocol and the different components of it. We'd like you to start hearing about the X3 HD of Hirvi Herdelman, and then the double ratchet, etc. And at the end of my presentation, we will look at what happened in January, where on the news we saw the backdoor or the vulnerability of the feature of WhatsApp. And who took us there? If we had to put a face to someone related to secure communication, what face would that be? Pop it up. So we are all in agreement. And if we talk about crypto, whose face is that? Okay, Alice and Bob. Alice and Bob, having recently concerns about quantic cryptography, let us see where it takes us, but we are still not there. I guess that you attended all the RootedCon editions and other conferences where there have been talks and presentation about WhatsApp. The situation is as follows. This is what WhatsApp asked us to do, find the X, and they said, well, the X is already there. As simple as that. The security that we had in WhatsApp in terms of encryption was nothing at the beginning, then RC4 that you could obtain with the password, and you associated with it, that was the level of technology and the security that we had. Lots has been said these days, and I have, well, quite a lot of experience. Sometimes you lose morale, you think that we are not getting anywhere, that there is no objective, that the children of my children and the children of the children of my children will have the chance to continue working in security if they so wish, but I'm not going to force them to do that because we are not learning from our mistakes. I don't think we should be as negative as that. We should always be hopeful. We should be hopeful as to what we are doing. So the situation in WhatsApp and level of security on WhatsApp is worse than that. The level of complexity in WhatsApp and the level of sophistication in WhatsApp is quite high. So we should bear that in mind. Also important, WhatsApp, and I understand I'm not in favor nor against WhatsApp, I'm just going to show you the state of the art. So WhatsApp wanted to bring to the masses a reasonable level of encryption. But that does not mean that that will make it the most secure IM app. For that, they have started to use the Signal protocol. We will be focusing on the Signal protocol. They started to use it at the end of last year, March. They also use noise protocol, and that does not mean, well, we will be focusing on end-to-end encryption, but that doesn't mean that there are no issues that we should be concerned about. We are using servers, messages go through servers, and servers are well aware of the origin, the destination, the users exchanging messages. They also know how often messages are exchanged. Also, we know the issues, security issues associated to SMS's messages, and also, well, the problem of stealing concepts. How do I verify the security key of the other end? So we will verify it through another channel. The Signal protocol is very much related to that. And actually, you know what animal is that? So I need you to pop it out. Axolotl in English. It is a species which is quite interesting. It's the power of danger of extinction. It is kind of an amphibious that it could end up being a gecko. It's like a fish with feet, and also very good at self-regeneration. And that's why we have chosen it for our presentation. And actually, I read that they can also regenerate the brain, so it has this self-healing capability. So why are we using or discussing the Signal protocol? Well, Signal protocol is becoming the security reference protocol for asynchronous instant messaging. That was adopted by WhatsApp last year before TechSecure Signal had it in Android and iOS, and now Facebook Message has also adopted it, as well as Google Allo, and as well as other Signal protocols and other variants of it starting to use it. So it seems that it will be the reference. What is the main objective? Well, the main objective is not trusting the servers in the middle, and that's why we are talking about end-to-end. And if some of our keys are compromised, the impact of that compromise is minimized. And that is the objective of that protocol. And for that, two sub-protocols will be used, X3DH and Double Ratchet. So who is to blame? Well, the Open Whisper system people, Trevor Perrin and his colleague, and that's it, and Moxie. So very brief introduction to crypto. I'd like you to bear in mind what it says there on the cartoon. We are using highly advanced crypto levels, but it says, who do you use it with? Well, I use it with my crypto people. So the idea is to mainstream the use of it. So first of all, Diffie Hellman, you know him already. So if you want to go deeper, I recommend you to visit projects and initiatives that we have implemented in Spain, which may be the TOF project by Jorge and Alfonso. Highly recommended if you want to learn more about crypto. So this protocol for the exchange of keys is aimed at a secure channel. Two users that cannot see each other cannot disclose secrets or share secrets in a secure manner. They do it through discrete logarithm, And we also see that in a very simple manner. So bear in mind that it is vulnerable to man-in-the-middle attacks. That is to say, it does not resolve the problem of you wondering or knowing for sure whom you are talking to. Alice and Bob reach an agreement about a number which is ideally would be above 1024 bits, and then they choose a secret. Alice chooses secret A, Bob chooses secret B, and Alice uses this number, prime number, and then the root component, and then they generate a public component which shows in capital letters, and they exchange A and B. And basically what both of them do is that whatever they get from each other, they put it to the power of the secret A, and Bob does exactly the same. It takes it to the power of B, and basically put into powers in to power. So leaves this result: alpha to the power of B and A multiplied by P, and then at the end of the day they both get the same value, which is the shared secret. Now they have a shared secret that they can use in cryptography and share it. So today we are talking about Diffie-Hellman. We are talking about the Diffie-Hellman key exchange. We are talking about it with ephemeral keys, not with long-term keys that are associated with me. I create a key to Diffie-Hellman, and I generate a key, a short-timed key. And we are also talking about elliptic curve. That is to say, same concept but different mathematical operations. So we are basically talking about the same thing in elliptic curve. I generate a secret and a key, private key for me to exchange information. The ones that are most used nowadays are the X255119 and X448. We will be focusing on the first one, which is used by the Signal protocol. So the second one is more robust, also slower. That's why we decided on the first one. So what can we say about 25519? It is important to differentiate. When we talk about the actual curve, we are talking about the mathematical curve that we use for our mathematical operation. And when we talk about the X and the number, we are talking about the exchange protocol. So bear in mind that we are all the time talking about 32 bytes, 256 bits. So we will be all the time handling secret and private keys of that size when they are small, 32 bytes. So the secret will be used to authenticate and to encrypt messages. What are the advantages of 25519? The advantage of it is it being really fast. You may see that on mobile devices or in CPUs, it goes really, really fast in generating keys, referring keys, and making calculations. And this is the curve that is being used, the reference to the prime number, 2 to the power of 255 minus 19, and with the base points equaling 9. So the use of elliptic curve in Diffie-Hellman does not resolve the initial problem of man-in-the-middle attacks that we mentioned before. What does it look like? Well, no changes. We have the two ends, Alice and Bob. They generate the secret parts with the curve, and the points base, they generate the public key. They exchange the public key. And again, we have this transitive property where the curve of my secret with the curve of his secret equals the curve of his secret with the curve of my secret. So at the end of the day, both end up in the same secret, having the same secret. So this is just the introduction. So I hope that you are ready for what comes next. Now, in terms of crypto properties. So these are the properties that we want to have. First of all, forward secrecy, then plausible denial, So I can go and say that I didn't send out anything. And then future secrecy. What is forward secrecy? Well, you will be getting this presentation if you want to dwell on that. But if you are, for instance, at this point in time, if someone compromises my keys, I just don't want that person to capture my private traffic and then to decrypt, decrypt all that private traffic. And what else can we say? Well, when we have a GPG, PGP, so you say, well, if someone sends out something signed to me, so that you can say, well, someone has sent it signed to me, and it was him because he's the only one who's got the private key. Here we are just looking for the opposite. So in my communication, I know that a person is sending communication to me. However, neither him or me cannot prove that it's being each other who sent it out to each other. So I cannot really go and say, well, yes, this came from RAUL. So we want the information that we exchange is more ephemeral. So this is basically about denying that I generated that. So this is about the use of ephemeral keys because the key that we refer is owned by both Bob and Alice. So Bob could sign something and may look like if it came from Alice. So actually he cannot say that that comes from Alice because he generated it because both are using the same key to generate that content from the viewpoints of encrypting it and from signing it. And then future secrecy, which is just the opposite of forward secrecy. Basically, it's as follows. If someone compromises me right now, that's why we have the axolotls. If someone compromises my keys, I just don't want this person to be able to encrypt all my traffic in the future. And that's why we have Diffie-Hellman now. And if you have seen mentions, forward secrecy comes from the protocol of silent cycle known as SKIN, and future secrecy comes from OTR of the record that I'm sure that you use it with Message Instant and Java, etc. So bear that in mind because we are not reinventing the wheel. So it means that someone had protocols before, well, we had existing protocols, and now we are mixing those protocols. Let us start with the protocol that allows us to establish encrypted, secure, asynchronous function. And then we will integrate it with double version. This is the triple Diffie-Hellman. So here, if you count, you can see 4 Diffie-Hellmans, but this dotted line is optional. What is this protocol aimed at? It is that Diffie-Hellman with or without elliptic curve aimed at exchanging keys. The objective of the protocol is that I speak or Alice talks to Bob and then they end up having a shared secret to authenticate the traffic and to encrypt the traffic. So the protocol will be based on the public and private keys of each end. It will give us all the properties that we mentioned before, together with the second protocol, the double rushed. And we want to establish a shared secrets in asynchronous environments. So that means that I want to establish a shared secret with another user, even if the user is not online. Alice wants to talk to Bob. Bob has his phone off, but despite that, Alice wants to establish that secure asynchronous channel to start exchanging messages in instant messaging. Well, this is the concept underlying this design. Well, the first thing that we find here is the egg and the chicken situation. So if I have to exchange a key to talk to you, but you are not there because you are offline, how can we exchange our keys? Therefore, I cannot send out a message because I cannot encrypt it with that key so that you read it later on. Well, they fixed it in a very simple manner. They did it by using a cache. Basically, a user, which is very part of the service, will publish a number of keys prior to the communication. They refer to the name as pre-keys, and they are single-use pre-keys, and they are left on the WhatsApp server. So whenever the user wants to talk to me, we'll use one of these pre-keys, even if I'm offline, and then the user will start the process. Of the secret that will be shared by the two of us. So this very first exchange of messages creates the encrypted session. So when Alice talks to Bob and they exchange messages and they establish that encrypted session, that is for life. When I say for life, I mean up until Alice or Bob reinstall the application or change the mobile device. But still, that what I mean is that it stays for quite some time. We need a server to input our keys. In this case, we have the WhatsApp servers, and for you to have a feel about the algorithms that are being used, on the one hand, we have the extended use of curve X25519, hash will be SHA-256, and in some algorithms for keys, string fixed text is being used, and different values will be given to it. Now let us move on to the most entertaining parts. Let us see how this works, step by step. So Bob comes and says, because I'm part of this communication ecosystem, I'm going to upload my keys to the server. And then Alice, when she wants to talk to Bob, gets the keys from the server, and then this X3DH process starts. That set of keys is known as the pre-key bundle. So this is the set of initial keys. So far, so good. Let's go for it. We have Alice and Bob. What will differentiate Alice from Bob? First of all, their identity key. These are the key. It's a couple of keys, public and private, associated between them. So remember, 32 bytes. Bob generates his key, sends it to the server, and then when SILES wants to talk to Bob, gets the key from the server. If Alice wanted to talk to Bob, she will send out the traffic encrypted with her key, and that would be it. That would be the simplified model of what we want to get. Well, the problem is that there is no forward secrecy, no future secrecy, no plausible denial. We don't have any of those properties. So therefore, now we will start adding components to that mechanism to improve it. And please remember, the Diffie-Hellman or elliptic curve system is TOEFL. That is to say, trust on first use. It is like SSH. The first time that I talk to you, that I speak with you, I want to confirm, I want to make sure that I'm talking to you. So therefore, what do we get from IK? IK allows us to identify the other user. Well, the disadvantage to it is that it lacks the other properties that we mentioned before. So if Bob generates a set of keys, a one-time key, well, he can take all these keys, upload them to the server, and by the time that Alice wants to talk to Bob, Alice gets the next available key, and then the server can delete the key because it has been used once, and then it has been assigned to Alice so that they engage in communication, and the rest of the keys will be used by other users who want to talk to you through these encrypted messages. And now Alice is in a position to talk to Bob.
Now, the same applies. Take a look about the forward concept. If I keep eliminating the keys, no one will be able to get those keys to then decode the traffic that was associated to those keys in the past. Okay? Bob can delete his and then start working from there. There is a problem with this. Bob could run out of one-time pre-keys. We have to see how to renew them. What could happen is that someone or attacks the server and produces a fake key to Alice. in order to mitigate that problem, we have a new key in the system. About keys, you get fed up with them. I'll talk about keys non-N. We have a pre-key, which we call the signed key, so that no one can impersonate that key. What do? I sign it with my private key. Because I sign it with my private key, it cannot be replaced. So I upload the entire batch so that when Alice, plus the single use key, so that when Alice takes everything, she can verify that it's me and no one can be in between and start talking to me. My objective here is to make you understand not just what keys we're using, but why the keys were included in designing the protocol. So from then on, we could do this exchange. Basically, what this allowed, what this prevented, is someone getting in between using keys that do not belong to Bob. Signatures. We're using XED DSA with DSA, okay, with curve 25519. In this process, this is the algorithm in use. And we'll now see this in its context. Bob has his key, his identity key. He signs one with the other, and that is sent to the server. A set of keys, single-use keys, are generated. They're all sent to the server, and that set of keys is what we call the pre-key bundle, each one identified by its values. What will Alice do? Alice must have an identity key, identifying her, of course. She creates an ephemeral key, a temporary key that she will use for this exchange process. And now we combine all those keys in the diagram we saw before with 3 or 4. This is the pre-key bundle for Bob. Identity, signature, and single use. These are the keys from Alice, identity and an ephemeral one. And we do 1, 2, 3, and if there is a single use key, a fourth diffie-Hellman. Because they were used at the server, there's none left. We would lose some of the properties we were looking for, but nothing too significant. With that calculation, there is a secret that can be shared. As we talked before, this is now applied to more keys so that we achieve those cryptographic properties. There is forward secrecy for this because this is ephemeral, an ephemeral key. It is not related to us by any means. Alice's identity key allows Bob to know that he is indeed talking to Alice and the other way around. She knows that she's talking to Bob. The signature key prevents anyone getting in between, injecting keys that don't belong to any of the two users. And the single-use key, the ephemeral key, is what gives me the most perfect forward secrecy, so to say. Okay? So with all that, we get to the secret. This allows me to use encoding. The first two give me mutual authentication with the identity keys. The other ones give me basically forward secrecy. How do you calculate the secret? In a very simple way. You take a function to derive keys. You do the four diffie-Hellman, you get the output. You get a larger number of bytes. And the derivation function gives me a secret, which is 32 bytes. And now, once Alice has the secret, what she can do is the output from each DH, she can forget about. She doesn't need it anymore. And the ephemeral key, she doesn't need it anymore either, the private part. This is the derivation function for the keys. Here you have all the details. It's an HMAC based key derivation function. Nothing especially relevant. We don't have the time to go into the details. Anyway, in the first message that Alice sends to Bob, she will need to send all the pieces of information so that Bob can do the same thing, so that he can apply the same exchange and then derive the same secret. Okay? So what does she need to send? The identity key. Well, any exchange of keys is from the public side. Of course, they have the private part for themselves. So they send their identity key. She sends the ephemeral key. She sends an ID so that Bob knows which one was given to her by the server so that he can check it in his list. And remember this one. Then it will encode data with something that is becoming really fashionable now. It's AEAD. This is authenticated encryption with associated data, okay? This is being used or will be used from April by TLS .3. In the associated data, I'm talking about the component to authenticate, we have the public keys for Alice and Bob, okay? So that you know about it. Doesn't make any sense to go into all the details, of course. So take a look at this. Alice had taken the pre-key bundle from Bob and had obtained the secret. Now Bob has to do the same thing. So Alice, in her initial message from X3DH, remember the private key is not needed anymore because she has a secret that was generated based on it. And in the initial message, she will send her public key, the ephemeral one, her identity key, and which one of the single-use keys she was given by the server. As it happens, when Bob gets all the details, she's got all the pieces in the puzzle, because he's got the identity key, he's got the single-use key, he knows which one it is, he gets the identity key from Alice and the ephemeral key from Alice, and he can do exactly the same calculation leading to the same secret. They now have a shared secret, and they're in the same situation as originally, but with the added properties in security, okay? He's not going to be needing the private part of the single-use key, so we get more forward secrecy. If we don't have the secret or the private key moving around, no one can steal it to decode my past traffic. So far, so good. Same associated set of data, and the rest is exactly the same. There's nothing special. So we have completed that protocol, X3DH. Is it okay until then? They now have a secret. This is just to have a secret between the two of them. Perfect. Any questions you might have? Well, they would need to buy their identity beforehand. The server might run out of single-use keys or reuse keys, something that is not advisable. Clients should not accept the same single-use key in more than one occasion. So a number of questions that are necessary for implementation to be correct. Perfect. And then the signature of the pre-signed key is submitted. If someone steals the ID key, that's it. Game over. Okay? We now move on to the second protocol, which will then be combined, the double ratchet protocol. I asked around. I didn't know as much about cryptography before, so I got in touch with people who know a lot about this. I got in touch with the experts, and I asked them, do we have a translation for this terminology, double ratchet in Spanish? It seemed that there was nothing. So I just translated it for doble carraca. It sounds really cool. We have two carracas moving. So I sent a tweet, and Julio said, how about trinquete? So I went to the Spanish dictionary, and I realized that it was only the green flap blocking the cog from moving in the other way around. And then Santiago and Guillermo said, how about engranaje? No, engranaje is only the cog, but the cog can rotate one way or another, okay? It is important that we remember this, because this is the goal for the algorithm. We will have two carracas, a double ratchet that will move in one direction and cannot come back in the opposite direction. They can only move in one direction. deriving keys. Okay? So double ratchet protocol overview. What will Alice and Bob do when they have a shared secret and they want to start exchanging messages? X3DH gave us a shared secret for an encoded session in the long term, but what double ratchet wants is exactly the opposite. The exchange of messages in a very short term where the keys are renewed very quickly. As you will see towards the end, we will have a key for each message exchanged, a different key. That is the ultimate goal of this protocol. So they will combine a Digi-Hellman double ratchet with a symmetric double ratchet. This is what we will see. Both of them have a secret, and Alice can send messages to Bob with a secret. Remember that, okay? That is the ultimate goal. We will see now how to implement this. It's a bit more complex. To set it up, we use two ratchets. One, a DH ratchet, which gives me future secrecy, and a symmetric ratchet, or a hash or immediate KDF, which gives me perfect or optimal forward secrecy. Okay? Remember what we saw before. With OTR, in Diffie-Hellman, we have future secrecy. With SCIM, or a symmetric ratchet, we have forward secrecy. With double ratchet, we have everything. If someone gets into my system and cannot compromise my keys, this is post-compromise security. To what extent you can keep security once you have been compromised, okay? Right, properties, very quickly. What they will do is generate a key for each message they exchange. This is the ultimate goal. And obviously the impossibility of knowing future keys from past keys. They will exchange the current Diffie-Hellman key, ensuring future secrecy, and then being more robust, in all senses. An essential element with this double ratchet protocol is how to derive keys from other keys. For that, we use key derivation functions. They have an input, they have a current key, that goes through the function, and we get an output. The output will be basically a key for the next step or the next iteration of the derivation function, and a key for the messages. Conceptually speaking, that's the goal. So we go step after step in this ratchet as we exchange messages. I think you're getting the message because it's quite simple. It's getting more complicated in a minute. So these derivation functions give me properties like resilience, forward secrecy, and future secrecy. It goes forward and backwards. An important thing to remember, each user will have three chains of key derivations. A root chain, a sending chain, and a receiving chain. As seems obvious, the sending chain for Alice is the receiving chain for Bob, and the other way round. And the sending chain for Bob is the receiving chain for Alice. Whatever is encoded by Bob can be decoded by Alice. So far, so good. So what do we have? Just to give you the context, so that we don't get lost. We have the signal protocol. We have the X3DH for derivation of the initial secret with the pre-keys for single use that we uploaded to the server beforehand. We now have double ratchet with two ratchets, symmetric and Diffie-Hellman. Okay? Right. So let's take a look at those two ratchets, symmetric and DH. The symmetric key ratchet is a hash function. It's like a pseudo-random generator with HMAC that generates keys. For each iteration, it generates the next key for that chain and a key for the message. Simple so far. Now, this ratchet has a problem. The problem is that if someone compromises one of those keys, because this is a function with constant input in time, it could compromise the rest of the keys towards the future, so it doesn't give you future secrecy as such. Do you understand that? To know what we need to add the other one, okay? This is a really good one for forward secrecy because this is a serial random function for hash in one direction only. So I may have that key, but I cannot go backwards. It's like SHA 256. There's no way to go back. That's the idea. We would compromise everything in the future if we only use that ratchet. That's why we use a double ratchet to start with. Let me give you an introduction to the second one, the second ratchet, which is the most complicated one, the Diffie-Hellman ratchet. When Alice and Bob exchange messages, they also exchange the current Diffie-Hellman keys. When Alice gets a message coming from Bob, she gets his DH key, Bob's DH key. With her own key, she can do an iteration, a Diffie-Hellman operation, and generate an output. That output will then be used in the root chain to derive the keys for sending and receiving. I'll give you details about that in a minute. So when Alice wants to send the first message, A1, it is received, and based on that chain, the first message is generated. This is the ratchet, the DH ratchet, so that the chains change their keys, and these are all symmetric ratchets, hash or derivation function, what we mentioned before. What these do is influence the input for the others, and the others evolve in sending each message. That's it. This is the ratchet we saw before with the derivation function for the keys. So take a look at the situation. Each user, Alice and Bob, starts exchanging messages with the other. In each message, they send the current DH public key, so the other user knows about it. When the other user receives it, if it's new, they do an iteration, generating a new set of keys that are different from the previous ones. That is the objective. So they have the DH key, they send it as part of the message, they allow the other user to do an iteration, and as part of that iteration, a new key is generated, and an output is produced. Perfect so far. What happens when Alice sends a message to Bob? Well, the same. This doesn't change. We have Bob. He generates his key. He sends his key to Alice. Alice generates a new key, does an iteration, generates the output, and in the next message, Alice sends her key to Bob, and Bob will do the same. So you see, this is what happens. It's like table tennis, okay? They keep exchanging keys from one side to another. Okay, now that we've reached this point, you should still be awake. So I would recommend that you go to the bar and take a break now. So a funny message and a funny image with table tennis. So I started looking for ping pong, table tennis. And I realized about the similarities between table tennis and the world of cryptography. In order for you to understand, you need to focus, to be heavily focused, like table tennis players. Sometimes your posture looks really awkward, DH, symmetric, and you need to take it seriously. You cannot go for a few drinks and then read the specifications and see if you can understand them, but really seriously. I mean, you have to be really serious, almost mad, okay? I have to understand this, come what may. But beware, if you focus too much, but I mean too much, you can reach this point. When you get silly, and it can get even worse, if you keep focusing, this I'm doing, no matter what. You need to take it with a pinch of salt, okay? You need to relax. You need to be a bit laid back. Are you paying attention? If you focus too much, things can go really badly, okay? And there's something else I wanted to mention. I know that we change with our age. As we age, we change. Can we learn about reverse engineering when you're 40 years old? Can you learn about cryptography when you're 40 years old? Well, there's no age limit. Neither for table tennis. It seemed to me, I saw something yesterday I didn't like. And RAUL told me they told me you have a reputation to keep, but there are limits, there are red lines, okay? I saw things I didn't like. People take table tennis or cryptography in an unusual way. Let us not assume that we know everything. We need to be humble, okay? So be careful who we play table tennis with. And then when we talk about cryptography, people may be interested in cryptography and they may be expert players in table tennis. And they take it quite seriously. I don't know if they use the right tools. I mean, that instrument that Obama is using, well, I guess there were others in that place, but they celebrate the victories in a very clear way. It seems they're having a good time anyway. And they get focused. They really focus on cryptography and table tennis. And you can find out whether there is a byte on that racket anyway. The similarities with table tennis. Okay, let's go to table tennis. Let's try and understand all of this DH ratchet that we have in front of us. Okay, a reminder after that break. Bob has his key, Alice has her key. Remember, Bob created his key, sent it to Alice. Alice uses that to do DH and get an output, okay, through one iteration. Right, what happens in the next step? When Alice wants to communicate with Bob, she sends him her DH key. That will allow Bob to do a ratchet of that DH with the previous key to have an output, which, funny enough, is the same output that Alice had calculated beforehand. So now they have something in common they can use to code and decode messages. But they're getting ready for the next iteration. So he will generate another DH key, do another iteration, generating a second output, which will leave everything ready for Alice to do the corresponding step and then code and decode again. Okay? I think it's simple to follow that. This is the iteration. In the next step, Bob sends his public key. Alice does an iteration of the previous DH, gets an output which coincides with the one from Bob. That allows her to generate a new key, to do another iteration and get ready for the next iteration from Bob, and so on and so forth to infinity. Remember that these are long-term sessions, okay? So this is the process, sends the key, does an iteration, coincides with the previous one. They can code, decode, gets ready for the next one in the next step. Right, you're getting the idea, yeah? Table tennis all over the place. In the DH ratchet. So what are these outputs? These outputs coming from the DH ratchet are not used to code and decode the messages. They are integrated in the chains. The DH outputs are used to derive, the sending key for Alice is the receiving key for Bob. Perfect. In the next iteration, we have the same. It keeps evolving. The next one for reception on Alice's side will be the one sent by Bob, and so on and so forth. So I'm getting ready for the next one. So when I need to send a message, I send it with this one. Bob can derive it and receives it with whatever he gets. Okay, so still playing table tennis. This is a simplification of the entire process, okay? But there's something else in between. The root chain that we mentioned before is in between. Take a look at this. We had this situation where I get a chain and I derive one for receiving and one for sending, but these are not there. These are taken somewhere else. In between, I have the root key, which we mentioned before, And it is the outputs of two iterations that give us the keys for receiving and sending. And why putting this in between? Well, we do the key derivations here, we do two iterations, and we get the final keys. This is done for different reasons, but above all because whoever initializes a root key is the secret that we got before in X3DH. So if we move backwards, we can trust the other side because that is based on a secret that was shared beforehand. So it is much more resilient, it is much more reliable for all the calculations that come later. That's what I explained there. Remember, the initial secret for X3DH goes into the root chain and allows us to derive the rest. Main benefits. Well, the explanation is here. We have combined the DH ratchet with the three chains, root, receiving, and sending. And receiving and sending are the derivation functions which combine with the input to the root key, allowing me to reach the end of the process. So let's put the two worlds together. X3DH, the original one we saw at the beginning of the talk, with that initial exchange so that the two users could derive a secret, integrated into the double ratchet. So there's two things that you need to take into account. One, the original secret from X3DH goes as an initial root key for the root chain to establish trust. And two, since Bob hadn't talked to Alice initially, the key for Bob, which is signed, is considered the first key for the DH chain for Alice. So that Alice has all the components to keep doing iterations from then on. So she does her iteration, derives the sending chain, and now has a key that can be used for the first message that she sends. That's the goal. So that first message, remember, must have two components. Everything Bob needs to get the green secret, the green initial secret, and the public key, the DH public key from Alice, so that Bob can initialize his ratchets and can move on in deriving keys. That is the process we see here. When Bob sends a first message to Alice, well, we know the dynamics that we have here. Okay, Alice does her ratchet to get the receiving chain to decode Bob's message, and does another ratchet for the sending chain. Here we're only seeing Alice's side. Bear in mind that we have Bob's side, who's doing more or less the same in a symmetric way. We're only seeing Alice and not Bob. Okay, bear that in mind. But let us take a look at this in context. Okay, Alice initializes a double ratchet protocol with that first exchange with Bob. She initializes a root chain with the secret, generates a key, does one iteration for DH, generating a key for the receiving chain. She does an iteration of the symmetric ratchets, generates the key for the first message from her, and she can send it now. What happens when Bob sends his first message? It allows Alice to do an iteration to derive the key for the reception chain and get the first message from Bob with the associated key, and do another iteration to get ready for the sending chain from now on. Just assume that at a certain point, Alice and Bob send messages simultaneously to each other. What would happen? Well, the DH chain would move on because they haven't got a message from the other side. What do? Well, I only make my symmetric part evolve.
Alice evolves or moves on chain number 2 to receive Bob's message, and that's the way it goes. A3, etc. A4, etc. And it will move on gradually. When Alice gets Bob's message, so it receives message B3, but because it can integrate its DH ratchet, a new set of chains is generated. and this ensures future secrecy. So she can do the iterations and receives messages 3 and 4 from Bob and continue sending out messages just in case Alice wants to continue sending messages. If we were to take a look at this together, and it would look like this. I did it by hand, and actually, well, so far we have seen this part, okay? This is Bob's part. So we are very close to the end. So I also would like you to bear in mind that this system allows messages to get lost or to be delayed. So if we wanted to do that, we would include in the number of messages in the current chain and the messages that we had in the previous chain. And those two values allow me to make this calculation very easily. So imagine that messages B2 and 3 from Bob were lost. And the next message received by Alex is B4. So B1 was the last message received by Alice, 2 and 3 lost, and she gets B4. Then she takes the steps, derives the chain, and then this says, I am message 1 of current change. So it starts to count from 0. So there was a chain 0 that I don't have. And now in the previous chain, there were 2 messages, because I know that in the previous chain I had 1. So I can go and say, well, I lost 1 from the previous chain and 1 from the current chain, therefore I have lost 2 messages. So what does Alice do? She evolves 2 messages on the chain, generates the keys on the chain, and stores them, just in case she needs them if she gets the messages later on. And therefore she can move on. She's in a position to decode before. Here, I know that this is before. The other 2 will not be lost. I'm storing the keys so that I can decode the messages in the future. And then, before we finish, we will take a look at how we encode messages. And before that, I'd like you to remember what happens with each time we exchange a message. So if I'm going to receive a message, I take a step in my receiving chain. And if I receive a new Diffie-Hellman key from the other user, what I do is to take a step in my double Rachet chain. Therefore, I'm generating a new structure, and that's the way I move on. So encrypting of messages, some details about the root algorithm. As I say, this is a derivation function. It generates 64 bytes because we have a receiving chain and then the next root chain, the key for the next root chain. Well, you know that already. And then in terms of send and receive chain, they use SHA-256 to generate the next chain key. And then it also uses a derivation function to generate the message key. And the message key is a bit more complex because it has 80 bytes. It has 32 for encryption, 32 for authentication, and 16 for initialization vector because it uses AES. So they use AES. They take the original plain text, and then with the encryption key, the text is encrypted. The message has the header with the public key that Alice and Bob are exchanging all the time, as well as the number for the lost messages together with the ciphertext. And so MAC authentication code is added to all that. It is based on a key and in the associated that we saw before, and the message. That is done for integrity reasons so that no one can change the message in the middle, in between. So this is how we close the loop of integrating all the elements. And bear in mind that if both have to exchange the messages, they will evolve, they will move forward in the exchange. And whenever there is an exchange of Diffie-Hellman keys exchange, then the chains move on, Diffie-Hellman chains move on. So 5 more minutes to tell you the following. So in January, The Guardian published a backdoor vulnerability bug or a feature on WhatsApp. We didn't know what they were they didn't know what they were talking about. Perhaps it was not a bug, it was a feature. And basically what we are saying here is the following. This initial exchange process is vulnerable to man-in-the-middle attacks because of the Diffie-Hellman. So it is important to validate that I'm talking to the person that I want to talk to. We can do that with a QR or with a 5-digit block. Here I am validating the identity key of the other user with his identity feature, which is his telephone number. What happened? Well, there was lots of controversy. The Guardian had to rectify. However, URLs never lie. The original URL said backdoor. So they referred to it as backdoor, and that's when the controversy started. So what about this retransmission vulnerability? Basically, it is as follows. Alice sends a message to Bob, and Bob is offline because he's traveling for whatever reason. Bob is not available, then the message will be sent. There will be a check, the message has been delivered, but Bob has not read it. What happens if Bob changes his keys? For instance, he reinstalls the app or changes his smartphone. Therefore, his identity key changes. So by the time Bob will go online again, considering the current situation with WhatsApp, WhatsApp will send out the messages to Bob with the new key. They will be encoded or will be encrypted. But what happens if what we have at the other end of the line is not Bob, but a third party, the government, or WhatsApp servers? Well, they could get an n number of messages that were in waiting while Bob was offline. And it is true that Alice will receive a notification saying that Bob has changed the key, but Alice receives this message after Bob receiving the messages. So this is a security trade-off. This is a balance between security and functionality. WhatsApp does it in one way, Signal does it in a different way. So WhatsApp refers to it as non-blocking. Security code says, well, if there are pending messages, just change your key. I'm not going to block your server with those messages. But in Signal, the security code change notification is a blocking one. So I'll show you an example. So we have Alice here. Alice has sent out a message, only one tick because Bob is offline. Then Bob comes back to life, 2 ticks, 2 checks. So the new Bob has received the message, and then, well, we get this notification message. Careful, the key has been changed. So Signal now, Alice sends a message, 1 check, then Bob comes back to life. And notice that there is still 1 check. And I said, well, the key of the user has changed. And here it is up to you to verify the new key. When you accept the new key, you will have the message will be delivered, and then 2 checks will be shown. So what do I recommend for more secure software? Also in this Reddit, I heard about dramatic messages about there not being any hope. So I think that we have made progress in terms of WhatsApp. So encryption, WhatsApp encryption is getting better. So I'm a bit hopeful. We are moving along the right direction, perhaps not as fast as we should, but we are making progress. So in my mind, what is most important is that you as a user have the possibility to customize the way your application works, customizability. What's being argued about WhatsApp? If we had a secure instant messaging app, if we wanted a secure instant messaging app, How do we want it to be? Well, someone said that we would like it to be open source, but not only that. So you really want to make reproducible builds. So if I compile code, MDH5, MDH6, the hash that is generated at that time for the binary should be the same that of the binary that I download. So, but that is not enough. But you actually go through the code of all that app. These apps are very, very complex. We may have that hope that the community will look into that code, but I think that would be complicated. And also very good to give the user the option, provided users with multiple security options. So basically, you want to have a menu asking you whether you want blocking or non-blocking, and then it's up to you to decide. And then the provider offers you opt-in or opt-out. So the user wants to have the option. And with this, we reach the end of the presentation. Is it clear? Yes, no, maybe? Well, I'm happy with yes and maybe answers. This is complex, explaining all this in an hour. It's a complicated thing. And if not, we will get to something like this. There is no audio, but then it says, is it clear? So, yes, sir. It's been clear. Pity that audio is not working. So you know that I always like to finish with Spanish sayings. So it says, do not stop coding today what you do not wait for tomorrow to code what you can code today. Lots and lots of references there available to you. Thank you very much for your attention, and I hope that you liked it.
Gracias. Es duro, lo sé, pero es que es así de complejo.
I know it is really hard, but it is as complex as this. All right, I'd like to start question and answers. Please correct me if I'm wrong. I'm going to make up a scenario. Raúl and Ramon, they want to share a secret from an IBIS 35 company when there are 35 million euros in stake, and there is a government interested in being awarded that contract. What about that government? Does it leave you DOS or me? Does it generate that message with a new key, sends out the message? And I assume that with that Rache sequence, we move on. Can I stop you from receiving notification of saying that the keys have been changed? I'm thinking about this scenario. So we have moved on to a new key, and I also have control over the app on your device. For whatever reason, Fugel and FASAP are two organizations in my territory, and I am putting out a tender against the Spanish company in a third country. Okay, give it a thought, think about it. Well, it is important. What we have in here is end-to-end encryption. Basically, this protects the following. It protects any interception or attack to modify the traffic in the middle. But if one of the ends has been compromised, I have one of the ends. I briefly discussed that with Trevor. So they mentioned brief compromise in the specification, and I said, what is a brief compromise? Well, they understood it as following. One of your keys is compromised, so therefore the algorithm self-recovers. And I said, what happens if I committed a key? That's because I went into your device. I will be compromising that key and future keys. But if one end is compromised, you are just dead. Questions now? Questions from the room? Hello, thank you very much for your talk. Okay, I hope my question is a logical question. Well, don't you worry if you cannot digest this information. One of the buts or caveats of the system is the following. In the first communication where the public key is sent, you are still blindly trusting that the person who sends out the key is the person he or she claims to be. Is the work, any work carrying out about system being based on blockchain technology and not that much in human trust? Well, I'm going to simplify this a lot. The initial problem of Diffie-Hellman, that is to say, I want to share a secret with you, and how do I know that it's you and not someone else? That ID verification that you do with QR of the code, that is done outside. We also had a problem some time ago with digital servers of X59 of web server, and that's where the certificate transparency is being implemented. That is to say, so that I know who is the holder of that certificate. There are some initiatives in that regard to generate repositories or directories for public keys, generic public keys in the world, which will be similar to what we have with GPG. When you have your GPG, you publish it in Red Iris servers or whatever for people to use it. But remember the problem that we also have with GPG. That's where you do the king's party. That is to say, you want to see the other person, you want to verify that that is his key and that no one has changed that key. Yes, there is work carried out in that regard. You are right. How do I know that your key is your key? And on top of that, moreover, every time you reinstall the app, that key will be changed. The secure model, it continues to be out of band. I call you, I read out the number, and you read out your number, because the number is made up by the identity keys of each of us, or we either see each other and we scan the QR codes. So this does not mean, well, some people say because this is a closed source app, how can you know that the key that is being used is the one, your one, and not an intermediate code that has been generated in the middle, which could also be the case. But you can only see that if you audit, after auditing the code. So thank you very much. Very interesting presentation. You've made a complex issue easy to follow. And I just would like to say that WhatsApp is included within the bug bounty of Facebook. So after this presentation, I encourage you to play around with it and to follow Piñalba steps. You will make lots of money. So everything is recorded, just to mention that to the human resources department of the company where Luz works. So please stand up so that we can see you. Once more, congratulations for your wonderful presentation about a very complex issue. Well, I hope that Luis Delgado is not in this room. So there is something in this process, and you are you've been tackling it now. So imagine that the server has been compromised. And often people do not have the show notification enabled, so that they will not see, they will not know that the key has been changed. In that scenario, simulating the man-in-the-middle attack, where we evidence that both telephones, every time they send out a message, it is like if they were reinstalling the WhatsApp or changing terminal. Is that possible? Yes, it is. That attack is feasible. Well, perhaps I went fast in my presentation. By default, notification of change of key are not by default in WhatsApp. They are enabled by default in Signal. That is a feasible solution. The argument that Moxie put forward, or the researcher that found that, is that in the design process, WhatsApp took into account that they just didn't want to be in a situation where from the servers they could know who has the notifications enabled or not. So they are putting themselves ahead of possible scenarios. So, for instance, there are regions in the world where people install and uninstall WhatsApp very, very frequently. They also thought about scenarios where we may have journalists or activists in places where there is lots of censorship. They wanted not to disclose or not to leave that information available from the server. Yes, in that case, yes, you are right. You could carry out an attack of that kind because notifications are not enabled by default. Right, that's another question about feasibility. It is the first time that I hear about double rushe. So when you said about losing some messages, so for instance, if I am establishing communication with you, could it be the case that I send out that you get a false message saying this is my message 1 million of the chain, but in the previous chain there were 2 million messages, so that you have to generate 3 million keys, store 3 million keys, and then overflow your app? Yes, that could happen. And to minimize it, they set up a maximum number of lost messages that you can handle, and that maximum number is 2,000 messages. Actually, I had a conversation with Jaime Sanchez, and he said, what happens with the communication from the user to the server? So we are talking about client to client or user to user. What happens with the server? So if we go back to the previous slides, the first one when I mentioned WhatsApp, I mentioned that very quickly because we just didn't have the time for it, would be the topic for one more presentation. So in the past, RC4 was used with the password on TLS, traffic ordinary HTTP traffic. So that has disappeared, and now noise protocol is being used. That has been designed by Treble Perrin, that we have used for double rushe protocol and for X3DH. So therefore, they are speaking using a different protocol, noise protocol. So we take one more question from the audience. Congratulations for your presentation, and especially because of the graphs and the images. I did not read the text. Very well-structured presentation. I appreciate that. My question is, what's your opinion about Telegram? Second question, WhatsApp or Telegram? And the third one, to talk with your grandmother, did you install Signal to her, or you continue to communicate with her on WhatsApp? Well, I answered the last question. I just don't have WhatsApp. I never had WhatsApp. And it is not because of the end-to-end encryption, which I believe is quite good, but just because of my contacts. I just don't want my contacts to be stolen, and that's the reason why I don't have WhatsApp. I have Telegram because in another conference I could not help by habit, but I don't allow Telegram to steal my contacts. Well, sometimes I'm going to situations where I cannot contact people because I cannot access to my contacts, and then I have to ask the other person to contact me. I've learned how to live with that. I cannot really tell you much more about Telegram because I have not looked into it a lot. Well, there has been a bug bounty to see whether someone could break it. And the good thing is that the protocol is open so that we can look into it. And it's not only Telegram. There are other instant messaging apps out there. So now with WhatsApp and end-to-end encryption, the security has been strengthened quite a lot now. So if we go back to my second or third presentation where I show slide when I showed Snowden, so there is a link from Electronic Frontier Foundation where they carried out the first analysis of the 6 or 7 or top IM apps, and they say that they will continue with the study, and they want to compare each of these top IM apps. I know that they are going very slowly because that's lots and lots of work. All right, it's a very, very last question. Okay, you have the right not to answer. If you had to decide between feature back or backdoor, well, what was released, it was not backdoor. They just introduced backdoor. I think the government was behind that. I wouldn't say it was a backdoor. To my mind, that was a vulnerability. That vulnerability can be fixed if your business model is the one that WhatsApp says. You fix it by adding a configuration option where I can choose blocking versus non-blocking. I hope, Luis, you agree with me. So thank you very much, Raul.